always like this. So if you have another one, then we will have the Bn equal to the G of n, or other basic possibly like that. And also we have mentioned that you can use those as a order list, A1, A2, A3, and so on. Start from the first elements to the second, third, and so on. You can try to go on that way. And we also mention about the general term of the sequence, or sometimes we call n term of the sequence as a an. Sometimes it is given to us in the explicit form, an is equal to the, for example, n plus 1 over n plus 2. Maybe sometimes not. We will see in the future. I mean, coming some of the slides is not given to us explicitly, but it is given as recursive. After that, we were able to generate a couple of terms, or some terms. For example, A1, A2, A3. So how do we generate those things? By ganti atau insert the n sama dengan number 1, number 2, atau 3, and so on. You will generate the terms of the sequences that we have seen. Actually, I have given you several examples of the sequences generate the first 5 terms. Then after that, we have mentioned about the convergence of the sequence. We say convergent sequence whose terms get closer and closer to some real numbers or some real number. The sequence, if it is like this, we call convergent. If it is not, we call divergent. Okay. Harap, everybody enter, because breaking is not good, and also I don't prefer this way. Next time I can start in this case earlier than that. Okay, never mind, then we will continue. Okay, we said convergent if the term, let's see. Okay, terms of the sequence getting closer to closer, some numbers when we basically proceed with the n large enough. That is the important word, large enough for the number. So we formalize those things in the following way. For example, okay, then we have the sequence. We call L is the limit of the sequence, or convergent to the limit L. Okay, for every epsilon there is a 1m or n. Yesterday I mentioned about the n actually, but it can be any positive number. Okay, integer, basically positive integer or natural numbers. So the distance between the an and the L, or terms of the sequences and the L, is very small. When was it? For all n greater than m. So meaning that yesterday I have explained also this, saying that finite of the terms out of the interval ln minus epsilon, the ls plus epsilon. How small epsilon is, even though greater than 0, but usually small number. If epsilon and smaller and smaller and smaller getting close to the 0, at that time this m will be bigger and bigger and bigger. So in other words, they are in terms of reciprocals, epsilon small or smaller, m getting bigger and bigger at that time. And we have mentioned this. And later on, we have also defined or provided this theorem saying that the limit operations among those or between the sequences, if an and the bn, they are convergent and they have the limit, okay, following way, then their addition, their multiplication, their division, and their scalar product also having the limit and the operation among the limit. You can see L plus minus K, L times K, C times L, or L over K. In here, in the others, we don't have any conditions, But in here, make sure that your Bn terms, they are not 0, and at the same time, limit of the Bn is not 0 as well. We have mentioned this. Maybe you can later on look at the proof of this theorem, which is I have sent just now as a whole chapter to you. Then you can study those details a little bit more. Okay. Then we have mentioned about the sequence theorem, because sometimes the calculation or computation of the limit is not enough clear. So we will try to make those, or at least have some idea whether they are convergent or not by using the squeeze theorem, or I mentioned sandwich theorem. What sandwich theorem was saying? Sandwich theorem was saying that if an and the bn convergent and the limit is common or same limit both, okay, then if there is any sequence between these two, you can see here an less or equal to the cn less or equal to the bn, then limit of the cn antara or between is the same as well. It was the Secuse theorem that I have given you one example during the yesterday class. Then when we look at the limit of the sequences, we will see, okay, some pattern. You can see, for example, 1 over 2, 3. I have given this example also yesterday. 2 over 3, 3 over 4, 4 over 5. And you will see that, and the trend of the terms getting closer to each other. You can see, for example, between the first term and the second term is bigger than the second term and the third term. You will see, for example, between here 0.15, here maybe 0.11, maybe here 0.10, around like this. I mean the distance between the A1 and the A2, or A2 and the A3, A3 and the A4 is getting smaller and smaller and smaller. But at the same time, terms of the sequences getting closer to the 1 as well. You can see here. Okay. Then starting from the 1 over 2, 2 over 3, 3 over 4, and 4 over 5, and so on. Goes on like this. Look like now you can see that 1 is the asymptote to do that limit or terms of the sequences. Okay, either you can use plotting here, graph of the like this, or you can use here as the interval that you can see, for example, A1, A2, A3, A4, and getting accumulated or dense around 1 or number 1, basically, or the real number 1. This is the convergency concept basically among the sequences. So therefore, after this, we will say limit of the sequence is 1. After this observation, we will be able to see limit of the an is 1. Okay, or you can write limit n over n plus 1 is 1. And don't forget here, remember, the limit concept or convergency concept is for large n goes to the infinity, n goes to the infinity basically. Okay, don't forget this. Okay, never mind. Then have a look at this one, for example. Determine whether the sequence is convergent or divergent. Can you look at it for this? For example, when you count the n 1, it will be negative 1. If you count the n 2, then you will have 1. Then you will have negative 1 again if you count the n equal to the 3. N equal to the 4 is 1 again. So this one or this sequence oscillates between the negative 1 and the 1, does not get in close and unique 1 number. Changes between 1 to the negative 1, 1 to the negative 1. So therefore this one is not convergent. You can see the elements or terms of the sequences like this. Around negative 1 like this for all the odd numbers or odd n, and for the even n you will see 2, 4, 6, and basically 2n or the even n, you will have the 1. So therefore this one is not convergent. Okay, never mind, I have similar. For example, you can see an is 1 over n converge to 0. You can, for example, start with the 1, then which is 1, then you continue, then 0.5, or 1 over 3, 0.33. Now what I mean here, now you can see the distance between the first term and the second term, 0.5. But between two terms, I mean the second term and the third term, you will see that getting closer and closer to each other. Okay, this is the attributes of the sequences or convergent sequences actually getting closer to the 0. Then you can see here basically the when as n grow, okay, bigger and bigger, value of the an getting smaller and smaller, 1 over n near to the 0, you can see here, for example. Okay, that is the graph of the or plotting the term sequences. Ada lagi orang? Oh, after 20 minutes. Okay, never mind. Just a moment, please. Okay. Then, sekali lagi, I will say, when n is getting larger and larger or bigger and bigger, tends to the infinity, value of the an is getting smaller and smaller to the 0 as. Okay, this is the convergency concept of this sequence. Or you can have the other sequences, for example, an is equal to the n square is divergent. Why? Because when n is growing, 1, 2, 3, 4, 5, then you will see that terms of the sequences getting bigger and bigger. Have a look at now. The distance between the 1 to the 4 is 3, and 4 to the 9 is 5, 9 to the 16 is 7, 16 to the 25 is getting grower and bigger and bigger. This is the attitude of the divergent sequence in this case. Okay, later on we will study concept of the increasing and decreasing functions or sequences concept, then you will understand maybe better. So there is a relationship between the boundedness and the convergency. So therefore we will say, so the sequence do not approach any number, basically goes up and up and up, goes to the infinity. Okay, one of your friends again asking me to Zuhaira. Okay. Okay. Sorry. Stuff. Okay, then this is the new today. I mean, we are starting tomorrow, basically with the new part. It was the revision of the previous part yesterday. Today we will say for any sequence, if it is, okay, nilai mutlak of the sequence is convergent to the 0, you can see here, nilai mutlak, okay, then limit of the an also 0 as well. But in here, in this particular theorem, saying that an is converge to 0 sahaja, other numbers doesn't give this guarantee. For example, if an convergent to the 1, we don't have. If, for example, convergent to the 2, we don't have. For example, 3, we don't have. Only for the 0. An, absolute value or nilai mutlak, converge to 0, then sequence itself is convergent to the 0 as well. Sequence itself is convergent to the 0 as well. So as a As an example to do this, we can try to see this one, for example. Limit n goes to the infinity, negative 1 power n, or negative 1 to the n, 1 over n. Okay, this you can see. Now when you pick up the absolute value of this, what you will have, basically you will have, because absolute value of the negative 1 is 1, so therefore, which is 1 over n. 1 over n is converged to 0, therefore all this sequence is convergent. Okay, similarly, you can look at this one, for example, but we don't have this guarantee. Okay, you can try to see, because this one converge nilai mutlak or absolute value of this sequence is n over n plus 1, which converges to 1 actually. So therefore, you have to be careful in this hypothesis of the theorem. Hypothesis of the theorem is saying if nilai mutlak of the an is 0, or limit of the an is 0, then the sequence is convergent to the 0 as well. It doesn't say any other numbers. Keep this one in your mind. But there is a one theorem related to this as well. If the function is continuous and the sequence is convergent, and the convergent of the L value or nilai, whatever you want to say, then f an, bila kita ganti an into the fungsi itu, then it is convergent, and the value is the fl. The particular example, you can try to look at it. For example, if we are trying to find the limit of the sine n pi over n, or similar, for example, you can try to consider sine n as a fungsi atau f, which is continuous everywhere. Sine function is continuous everywhere, and your sequence is pi over n, which is also convergent to the 0. Then f(an) is the sine pi over n is convergent to the sine 0, which is 0 as well. Let me see, someone is coming again. Who is this? Aida Shamimi. Okay. Just a moment, please. Okay. Then this is the example that I have given here. I mean, you can imagine other examples or try to make or construct your own examples, as long as function is continuous, sequence is convergent, then your f(an) is also convergent, f(an). So maksudnya kita ganti sequence itu or substitute inside the fungsi, like the sine pi over n, like this. Okay, after that, I have mentioned sometimes formula is not clear or explicitly given to us. So we have to generate the rest of the terms. Maybe some of them is given to us. After that, we have to generate and try to get the formulation or general term from that. This kind of sequence is called the recursive sequences, or recursive definition, or recursion formula, basically. In other words, specifying the sum or first few terms of the sequence, using the formula to specify the coming terms or subsequent terms in the terms of the preceding terms, meaning that we will be using the previous terms to generate the coming terms. Like, for example, here, if you look at, find the first 4 terms of the sequence. First term is given by like this, and the an is 2an minus 1 plus 1. 2an minus 1 plus 1. So what does it mean this? A1 is 4. A2, in order to generate the A2, we ganti an minus 1, the previous one, which is A1 plus 1. So like this, A2, we will generate, or we will be able to get out 2 times A1 plus 1. which is 9. Or A3 is equal to the 2 times A2 plus 1. As you can see here, this time A theta is the AN. So the previous one is the A2. This is the one. For A4, in order to generate the A4, we have to use the A theta and so on. You can try to generate more and more. So this kind of sequence is called recursive sequences. The AN is not given like the 1 over n or n over n plus 1 or sine pi over n or others. So AN is given in terms of previous terms or previous term in here particularly. For example, another one is the very famous one. Okay, you try to find, for example, this kind of sequence general term. It is given 1, 1, 2, 3, 5, 8, 13, 21, and so on. Goes on this way. So, macam mana we try to, formulation is not given to us. So, as you know, this is the very particular one. The F1 or A1 is 1, A2 is 1, A3 is 2, A4 is 3, A5 is 5, and so on. So when you look at the terms of the sequences designed in a way that the Fn is given by Fn minus 1 plus the Fn minus 2. Maksudnya in here, in this particular example, to generate the further terms, we have to use the previous two terms, next previous two terms. For example, in order to generate the 13, we don't use anymore 1 and 1. We use 8 plus 5, which is 13, like this. 21, also similar, 13 plus the 8. So this is the general formula given by, addition of the two previous terms. We call this kind of things is, recursive. And this is well-known sequence is called the Fibonacci. I don't know whether you have heard about it. This sequence, 13th century Italian mathematician known as the Fibonacci. It is given that way. How about the other one? First one is given as a 1, and the other one is given an minus 1 plus 1. That look like the previous example. You can try to generate, or similar, for example, you can have a1 equal to the 1, an is given n times an minus 1. Okay, all these are 1, 2, 3, all these are given as a recursive definition. Later on, we will study macam mana limit of the recursive sequences. Okay, never mind. Now I will ask you provide those answer for, and you can submit to my email. Write first 5 terms of each sequence in explicit form. Explicit form. Apa maksud? Meaning that try to find the A1, A2, A3, A4, and A5. Similar for the others as well. But the other one, find the third, fourth, and the fifth terms of each. They are recursive ones. Okay, I will give you 5 minutes to answer those questions, and you will try to submit to my email. You know my email, right? Okay, please go ahead and try to answer those questions. And I can basically send you my email through the chat. Let me see. Okay, this is my akilichman@yahoo.com. You can try to send your answer to this email. I will give you 5 minutes. Okay, 5 minutes only. After that, I will continue back. And at the same time, I want to look at your email or your phone basically through this way as an attendance. Later on, I will take it. Okay, please go ahead and try to settle your answer and send to me now. Oke, sudah? Macam mana? 5 menit sudah habis. So, I'm sure you have sent jawaban. So, we will continue today. I mean, after this, again, our class by continuing this called, okay, monotone sequences or monotonic sequences. What does it mean? A sequence is we call monotone or monotonic when we have the relationship among those terms. Terms are non-decreasing. You can see here, for example, A1 less or equal to the A2. These are the terms of the sequences. So relationship among the terms of the sequences is in this way, monotonic, or other way also possible. A1 lebih besar daripada A2, A3, and so on. So either of it satisfied by the AN, we call them sequences monotone or monotonic sequences. And another concept here is the bounded above or bounded below. These are the new concepts that you should study basically in detail. So we call a sequence bounded above if there is a real number n such that terms of the sequences n less or equal to n for all n. Keep this one in your mind. Okay, keep this one in your mind. An is bounded by n for all n. There is no exceptional case. All of them is, I mean, A1 less than M, A2 less than M, A3 less than M, AN less than M. AN plus 1 is less than M as well for all n. So we call that number as the upper bound for the sequence. Similarly, we call AN is bounded below if there is a real number. Again, all terms of the sequences is bigger than that number. In other words, n is less than a1, a2 is less than, greater than n, or n less than a2, n less than a3, n less than a4, and so on. Sorry, for all n. At that time, we call this number n, capital N, as a lower bound of the sequence. Now, if both of them satisfied at the same time by the sequence or our sequence, a sequence AN is called bounded if it is bounded above and bounded below together, both of them, not only one-sided, both-sided. Bounded above is one side, atas ada limitation, bounded below, bawah ada limitation, but when we say bounded, both sides ada limitation or bounded between two numbers basically. So then we can try to see, for example, AN is bounded above, then you can see here particularly, I mean as a contour, then all the terms of the sequence is getting closer and closer to the one. So 1 is the upper bound for this particular sequence. Okay, 1 is upper bound for this sequence. So AN all, okay, less or equal to the M for all N. You can see all the terms of the pink, okay, dots less than the some number which is M. Here you can consider as a 1, as a M in this particular one. Okay, so M is upper bound. So have a look at this, whether this N over N plus 1 is bounded above by any number greater than 1. In this case, the terms of the sequences is getting closer to 1 as well, but this time 1 over 2, 2 over 3, 3 over 4, and so on. Is again, this is also AN 1.1 is upper bound for this. Okay, but 1.001 also, okay, upper bound for this. So which one is the smaller one we will take that one as a least upper bound. Least upper bound. Later on, you will see this one as a supremum in your real analysis class. M is equal to the 1 as a least upper bound, the smallest upper bound, because n over n plus 1 getting closer to 1, and never pick up the 1 as a value, limit value, yes, and goes to the infinity. N over n plus 1 is near to the 1, but never equal to the 1. So we will be able to consider m as equal to the 1 as an upper bound or least upper bound. As you can see here, there are many upper bound actually. Okay. Then if m is an upper bound but no number less than m is an upper bound, then m is called the least upper bound. Sekali lagi, m is an upper bound but no number less than m is a new upper bound. Tak ada lagi smaller than that. Then m is called the least upper bound here. Okay. Another one is bounded from the below. Again, you can see this time. This is the upper bound. This is the lower bound. You can see here. Term of two sequences is getting closer to the asymptotic line like this, or m basically. In this case, we call the lower bound. Similarly, you can do here, for example, you can pick up an greater than 3. At the same time, okay, for example, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over, and so on, getting closer to the 3 actually by adding those numbers, but the lowest one will be the 3 actually. Okay. Then if m is a lower bound, but no number greater than the m is a lower bound again, then m is called the greatest lower bound. Greatest lower bound, meaning that all the terms of the an is greater than 3 basically. That is the one. So greatest upper bound in here is 3 basically. Now there is a one. Again, summary of altogether, an is bounded from above and below, then an is bounded. That we have studied, in the previous slides as well as an explanation. So if an is not bounded, then it is called unbounded. Unbounded. Later on, we will see the relationship between the convergency and the this concept. Every convergent sequence is bounded. Every divergent sequence is, or any unbounded sequence is divergent. Later on, we will see some examples. Now, the relationship between the boundedness together, monotone, then equivalent to the convergency. In other words, when we are trying to see whether sequence is convergent or not, sometimes we will look at whether sequence is convergent or and monotone. Together, it is convergent. This is one of the great theorem in analysis or calculus, basically. Later on, you will study those things. Now, the concept around here now to continue with the terms of the sequences. What we will do now, consider we have a sequence A1, A2, A3, and so on. If we add the terms of the sequence, what will happen? In other words, A1 tambah A2 tambah A3 tambah AN all together, for example. What will happen? This is the goal. Okay, sequences added up together generate a new concept we call the series. Okay, first n terms of the sequence is called the partial sum that we will try to see. But it is very customary to write those things A1 plus A2 plus A3 and AN. Okay, is not good listing all infinitely many numbers. So we will use the one sigma sign or letter or symbol. We call the sigma. Okay, we will use the sigma notation to represent the series. Then later on, we will study concept of the convergence again as well. So what does it mean now? I start from the 1 to the n, meaning that Kitaganti I here as a A1 plus A2 plus A3 plus A, and so on, goes on. Meaning that adding up the terms of the sequence of the AI, beginning with the first term and ending with the n term. If it is here finite, well, then we will put the n term. And I is called the index of the summations. Okay, this is the concept basically. In other words, we are trying to write the Sn or partial sum as the A1 plus A2 plus A3 and so on, represented by the I from 1 to the n AI. And if it goes infinitely many, doesn't stop in the some places like in the previous one, we call that infinite series. That is the expression goes on here. You can see n finite here until n, but in here s goes to infinity a1, a plus a2 plus a3 plus an plus dot dot dot, meaning that some bone like an plus 1 plus an plus 2 plus an plus 3 and so on, goes on infinitely many. So I from 1 to the infinity ai again. So 1 is finite if it is number stop in somewhere. If it is goes on further and further, that is infinite. Okay, this is the generation or construction of the series by using the sequences. So now we can try to look at, for example, particular examples, how to evaluate. Yes, please. Is it missing something? This one doesn't come? Oh, how come? Just a one. I'm surprised. Supposed to be same. Just a moment. Is it now? I will move, and whether it's moving or not. Just a moment. Is it moving now? Enough? Moving? Okay. Okay, perfect. Thank you very much for your warning. Okay, otherwise I wouldn't know. To be honest, I thought it is moving. I can do PDF, but I want to show you step by step. That's why sometimes I don't use directly PDF. Okay, never mind. The boundedness already we have studied. After that, we will try to generate or construct the series by using the terms of the sequences, adding up or summation or sum up altogether. And we use, because writing all the time summation from 1 to the infinity, too many, so we will use the notation of the sigma, or we call that one as sigma Greek letter. And that is the one. If we stop in the finite place or some n, stop in there, we call finite series. If goes on infinite series. Okay, then we can try to evaluate those values. For example, what does it mean? K from 1 to the 6 to a quasi k plus 1, meaning that V Ganti k with the 1, you can see here, 2 to the power 1 plus 1. The second one is that at that time kita ganti k 2 kuasa 2 plus 1 plus k 3 k 3 2 kuasa 3 plus 1 and plus 2 kuasa 4 plus 1 and so on. You can see here we are adding, meaning that ganti k starting with the 1 until 6 atau okay, enam all together, and we sum up all together. You will see that with the, which is this number. Another one is j started from the 3. In here you can see k started from 1. Here j started from 3. So we don't have any basically rules starting from the 0 or 1 or 2 or 3. Depends on the situation. For example, if it is given to us like this, J tiga to do 6 only, meaning that A3, A4, A5, and the A6 sahaja. Itu ja. At that time, we will use the notations. Okay. So what does it mean now? For example, somebody asks you K from 2 to the 6. K, what does it mean now? Meaning that K start with the 2, 2 plus 3 plus 4 plus 5 plus 6 is like this. So you can try to, okay, generate the others as well. Okay. And similarly, you can try to put here, for example, N3, kala N3, 4 kali 12 tolak 7 jadi 5. Plus 4 times 4 is 16 tolak 7 9. And so on. You can try to write those right hand side by using the summation formula. Okay, similarly, you can do this k from 1 to the 5, 4 power k or 4 to the k. Again, 4 to the 1 plus 4 to the 2 plus 4 to the 3 plus 4 to the 5 again. Okay, then we have some summation properties, but I will give you maybe 5 minutes break, then we will come back. Okay, then I will continue with the summation of the operation of the summations or properties of the summations. Okay, now you can have the 5 minutes break. We will continue at basically 1 o'clock. Is that okay? Yeah, okay, no problem. I will come back in 5 minutes time. Tiga orang sahaja hantar answer atau jawapan. And the name Nur Afrina, Imtinan, and the Fatma Kahar. 3 orang sahaja. Yang lain belum. Padahal sudah tamat masa. Kenapa masa itu you buat apa? Never mind. I will try to continue now. Class back again. Okay, let's see what we can do. Okay, the operations with the summations of the terms of the sequences or series, basically, we can do similar operations that we used to do with the functions. Don't get panic when you see the series. Actually, they are the summation or added up of those sequences. Okay, just a moment, please. Okay. Now you can see summation properties. Now, if we have A1, A2, A3, AN as a one sequence, and another one is B1, B2, B3, and the Bn are one other sequence together, and the C is a constant and a number, meaning that real number, then for every positive integer, you have this relationship. In other words, if your sequence are the constant, summation of the series is equal to the number kali the C. So upper bound of this basically C times N times C. Okay, this is the one. Another one, meaning that C times AI, then you can keluarkan, since C is not depends on the index. So it is bebas dari I, so therefore can go out. So therefore then you will have this C times all summation, rather than here in the first one, you will apply C to the each terms of the sequence. C times A1, C times A2, C times A3, C times A4, and so on. And actually is the same by saying that C times A1 plus A2 plus A3 plus A plus AN, like this. Similarly, you can at the same time add the same indexes, okay? You cannot add A1 to the A5 like that. In here, A1 plus B1 or A1 minus B1 like this. You can do the term-wise operations. Okay, this is the properties that we have. Some rules, these kind of rules actually sometimes help us to solve some complex problem. For example, if I ask you to find the first 1,000 numbers summations, let's say, for example, from 1 to do 1,000, someone has to find the summation. It will take ages to write down all together, but this kind of formula will help you to find, for example, 1 from 1 to the n, I equal to the 1 plus 2 plus 3 plus n. So if we say, for example, until 5, meaning that n is 5, or until 100, n is 100. If, for example, n is 1,000, n is 1,000 here as well. So at that time, you will see the n times n plus 1 over 2. I don't know whether you have studied induction method atau proof technique or kaidah induksi. This is the one that can try to help us to prove some of the theorems like this. Okay. Similarly, for example, I square. If somebody give you, say that, okay, find the 1,000 square addition up all together. I'm sure again it will be so complex. I mean, it takes so long to find out what is the basically 1 square plus 2 square plus 3 square plus 1,000 square. And again, you can verify this formula saying that, okay, sama dengan n plus 1 or times 2n plus 1 over 6. Okay, this is the formula to find the square of the summations. And if you try to find the cube, and for example, you try to find the fourth kelas 4, Never mind. The cubed is 1 cube plus 2 cube plus n cube is equal to the n square n plus 1 square over 4 and so on. These are the some rules that it will help us to find the summation of the or numbers 1 to n 1 to 1 square n square or 1 cube to the n cube all together. Okay, never mind. Use summation properties to evaluate this I from 1 to the 45. I mean the sequence is 5 from 1 to the 40. Then the rules will make our life easy, meaning that I from 1 to the 45 meaning equal to the 40 times 5, which is 200. Try to do the other one and find the B and the C together. Okay, B is meaning that here kita keluarkan 2 because 2 tak ada kena-mena dengan I. Ini 2 kali I. So therefore 2 bebas daripada I. So then 2 kali, the other one is from 1 to 22. Hey, don't say that it is easy. No, 1 plus 2 plus 3 plus until 22. I'm sure it will take at least 5 minutes to calculate those things. But when you use the rule and the regulations, then it is easy for us. N times n plus 1 over 2 is like this. Similarly, you can apply, this time you can see here, we have the cube, the square. Square is lagi basically canggih sangat, so therefore it will take longer time. Then you can try to use the regulations or rules of the summation that in the previous one we have seen like this. Then you can try to apply. But when you try to apply, for example, you have to here be careful. For example, you pecah dulu 2 kali I square minus 3 is like this. Then after that you apply the rule again to do this previous one and rule again to do last part as well. Then you will see all together. So this part is coming from the square root, square side, and this one is coming from the 3 kali 14 side, or from 1 to the 4 plus 3 side. Okay, this is the basically helping us to find the complex summations or computations. Okay, so therefore now we will try to say that represent the sum of the terms in a sequence is called the infinite series. So now we want to know if the series converges to a single value or there is a finite sum, meaning that the question in these sequences convergency matter. We try to make useful things only through the convergency. Okay, and later on we will study equivalent forms of those, like the monotone and bounded. This is the equivalent form of the convergency. Similar concept is coming to do basically series as well. But the series are always, okay, the summation of those things. And we want to see whether it is getting close to any number. For example, n from 1 to the infinity, 1 over 2 to the power n, meaning 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16. Siapa boleh cakap yang ini berapa biasanya? Okay, you ini 0.5, ini 0.25, ini 0. Basically 15 or maybe 13 or 12, basic 12 and a half possibly. Okay, then see all together, add up all together to up to infinity, until infinity, and try to tell me what is this. Later on, in order to find this kind of things, we will try to classify the series as a, harmonic series, telescopic series, or geometric series, and so on. This kind of things that we want to uji atau test or examine whether they are convergent. So n from 1 to the infinity, meaning that 1 plus 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 goes on like that. So the series diverges. This one is divergent because you can see Sn is equal to the n, meaning that multiply n times 1. If n goes to the infinity, then basically summation goes to the infinity as well. Even though this is the constant sequence which is convergent, but the series divergent. Okay, be careful in this case. Okay, never mind. How about this? 1 over n plus 1. What do you think? Okay, when we look at like this, then we will see 1 over 2, 1 over 6, 1 over 12, plus 1 over 20, and so on, plus, plus, plus. Who can tell me whether this sequence, sorry, this series is convergent? Convergent meaning that tends to some numbers, finite numbers, like 1, 2, 3, 4, 5, 26, 100, maybe 1 million, some numbers sahaja. Can you identify this? So what we will do, we will try to write them in a way. For example, if you look at the first term is the 1 over 2, 1, n is 1, s is 2. It's n plus 1 is 2. Then second one is 2 over 3. And third one is 3 over 4. And another one is like this and goes on, n over n plus 1 altogether. Yes, please. Again, Ya Allah, Ya Tuhan. What is wrong? Adahan to the Katsinika. Now, can you see now? Okay, let's continue. In this case, okay, I'm sorry. Something wrong, I don't know. I mean, program is not giving me any signal around here that doesn't move or anything. Only you are the one observing and monitoring my movement. Okay, never mind. The first term is 1 over 2. Second term is 1 over 2 plus 1 over 6. That is the or in the series, meaning that first one is the first term of the sequence, but the second one is added together. That is the one. And third one is all together 1, 2, 3 terms together, which is this. And the rest is like this, that we will have. So n over n plus 1. Then you can try to, if the sequence of the partial sums convergent, the series convergent, meaning that if this summation is convergent, okay, then it is, the series is convergent basically. So therefore, you can try to look at the 1 over 2, 2 over 3, 3 over 4, 4 over 5, and so on. Okay, goes on like this. The converges to 1, so series converges. Series convergence. Okay. Look, later on we will study looking at the around here only, the general term of the series or sequences basically. For example, is given, look at partial sum, we formulate as n over n plus 1. Macam mana saya tahu atas itu 1, 2, 3, 4, 5, and so on. Berapa kali? Okay, n kali. Bawah itu n plus 1. Like that. So this one is convergent, converges to 1. So therefore this series is convergent as well. But we don't know the value yet. So what is that number, that series convergent? So we will try to now find that one. Okay, how to find that one? We will write this one in terms of partial fractions that you have studied already. We can use the partial fractions 1 over n plus 1 in the following way. It is 1 over n minus 1 over n plus 1 is the same as 1 over n times n plus 1. This is the summations. In other words, a over n plus b over n plus 1. Then you try to find the a and b later on. So then when you find the a and b, you will see a is 1, B is negative 1. It's like this. So then when you look at it, this is equivalent exactly or equal to the same number like this. So 1, 1 minus 2, 1 over 2 minus 1 over 3, and so on. We combine them. For example, n is 1, 1, n is 2, 2, n is 3 is this, n is 4 is further, and so on. So terms of 2. Now when you look at these sequences of the or summation, you will see that 1 plus 1 minus, 1 plus 1 minus, 1 plus 1 minus, 1 plus 1 minus will cancel out. Apa tinggaldı kaç sana? Apa tinggaldı kaç sana? Basically first one and the last one, which is 1 minus 1 over n plus 1. So when you try to take the limit and goes to the infinity is the 1. So this summation is equal to the 1 basically. This is the cara finding the limit of the series or the summation of the series. Okay. How about this? Sorry, we have studied already this. Now if you look at it, then you will see, okay, that is the limit of the basically value that we have seen just now in the n over n plus 1 is the summation at that time you reach to the 1 actually. Okay, now our mind, then there is a particular sequences that I have mentioned which is called, okay, geometric sequence. What does it mean? The terms of the sequences are based with the some common ratio. For example, this is 1 over 2, another one is 1 over 4. So ada kaitan dengan previous one. Also same as well 1 over 8. You can see 1 over 4 is generated by multiplying the 1 over 2 by the some numbers, which is 1 over 2. Then when you try to multiply the second terms by the 1 over 2, okay, and then you will have the 1 over 8. Similar, the rest you can generate or produce. Okay, so we call that number is common ratio. Is the same antara between, meaning that you divide by first term and the second term and the third term and the fourth term, and so on. Each term is obtained from the preceding number by multiplying by the same number, which is r. Okay, in here, in this particular case, is 1 over 2. Okay, find the r in this case is called the common ratio. Common ratio. For example, if it is given like this, 1 over 5, 1 over 2, 5, 1 over 25, and so on, try to find the r. Then you can see that again, which is, okay, the multiple of the 1 over 5, actually. Okay, or the other one, 3, 2 over 3, 4 over 3, 8 over 3, and so on. This is also another one of the geometric series. The difference between, again, the 2 times, 2 times, 2 times, and so on. Okay, so we call this kind of series is a geometric series. In other words, there is a one first term or constant term, then there is a common ratio. So we generate the rest of the sequences, okay, by playing with the common ratio R kuasa 1, R kuasa 2, R kuasa 3, R kuasa 4, and so on. So as long as in the geometric series you know the one or first term and the common ratio, then you will be able to examine your series in the geometric series. So we write them, for example, in here, in this particular case, in the following way. 1 over 2 is the first term. 1 over 2 is the common ratio between all those. I mean, you generate 1 over 4 by multiplying the 1 over 2. This is the one. So quasi n minus 1. So this series represented by these summations. Okay. And similarly, you can have, for example, some more again multiply by those numbers. For example, 3 over 5 is your first term. Then you multiply each term by the negative 4 over 5. Then this is your common ratio and the quasi n minus 1. Similar, you can have more and more. Kalini, you can see here, the first term is 2 over 3. Second one is the 2 times 2 over 3, which is 4 over 3. So in other words, you will be able to write in this form. First term is 2 over 3, 2 or 2 quasi n minus 1. These are you can see, this 1 over 2 common to everybody. Negative 4 over 5 common to everybody. 2 common to everybody. So we call this one is common ratio. Common ratio. You will get, okay, dividing by between the terms A1 over A2, A2 over A3, A3 over A4, and so on. It's like that. Okay, macam mana sekarang summation of the geometric series when we look at it?
Prof, slide Prof start lagi.
Allahumma salli ala Sayyidina Muhammad. Okay, just a moment. Did you see this one? Did you see this one just now?
Can.
You have seen this one. I mean, in the previous slide, stuck in where? In here or previous one?
Previous one.
Or previous one in here? You mean here? Or this one? Ya Allah. In here? No. Astaghfirullah Nazim. Okay, just that one. Can you see my slide now? Which one is your? Is this one?
That's right, 35.
35. Okay. Now I am trying to make the animation of the slide show of the 35. This is the one, right? Ini jelas? Sudah belajar? Then I will go to the next one, infinite series, and we will try to see whether they are convergent or not. If it is convergent, it is useful for us. If it is divergent, we cannot do or manipulate the infinity basically. So therefore, we look at their characteristic, whether they are convergent or not. But there are some criteria for this that we want to study. Okay, if finite, the summation is finite, then it is convergent. If summation is infinite, then divergent. So therefore now, this series is walaupun the sequence is constant sequence is 1, but the series is basically diverges because summation of the partial is n. When you take the limit n goes to the infinity, Sn is equal to the infinity. So therefore, this very simple, okay, series is not convergent. So sometimes convergent sequences does not produce the convergent series. Then later on, we will study this concept actually. Okay, then we have provided this partial sum that we said, okay, the first one is the first terms of the sequence and the partial summation is the same. But the second partial summation is the summation of the first term and the second term of the sequence. These are the terms of the sequences, but added up, or we sum up them together. Then S2 is 2 over 3. Then S3 is 3 over 4 we had. Then, and together, when you look at the 1 over 2, 2 over 3, 3 over 4, meaning that we will have the n over n plus 1. This is the partial sum is n over n plus 1. So partial sum is convergent. If the sequence of the partial sums converges, the series converges. So therefore, in this particular case, sequences in this form, 1 over 2, 2 over 3, and n over n plus 1. When you look at n over n plus 1, convergent, and the limit value is the 1. So therefore, your series is also convergent in this particular case. I'm not saying, okay, this n over n plus 1 is the sequence. It is the summation of the partial elements or members. I mean, we sum up together all, then give us n over n plus 1. Now, if you come to here, for example, n over n plus 1 is no longer convergent. Later on, we will study this. So we look at the partial sum of the terms of sequences. It's like that. Okay, then later on, we study this, how to find the summation. We said just now, converge to the 1. So we put them together by using the partial fractions, and we write them in the following form. I said, if you want to write partial fractions, you will write 1 over n plus 1 equal to the a over n plus b over n plus 1. Then we will try to find the a and b. When you try to find the a and b, you will see a is 1, b is negative 1. I have mentioned this. So you can generate now Ganti n is equal to the 1 over 1 is 1. Ganti n is 1 over 1 plus 1, which is 1 over 2. Then second one is n2, 1 over 2, minus 1 over 2 plus 1, which is 3. And so on. You can generate the rest of the elements of the series. Then when you look at all together, you will see that, as I mentioned, 1 is minus, 1 is plus, 1 is minus, 1 is plus, 1 is minus, 1 is plus. So those minus plus, they will cancel out like this. Okay, they will cancel out like that. Then rest tinggal sahaja is 1 minus 1 over n plus 1, which is the same actually that. So therefore, taking the limit of the last part is equal to the summation of the series, which is 1. So therefore, you can say, try to look at and saying that, okay, starting with the 1 over 2, okay, then 1 over 6 or 1 over, you can have it, and you will see that this is the limit. Summations, or the limit is the limit, sorry, the value of the series is equal to the limit of the partial sum. Okay, we have studied. Then I said, this is not easy all the time to examine whether convergent or not. So we will look at this series in different way, or we try to classify. One of the way, for example, classification is looking at geometric series structure. Geometric series structure is telling us the terms of the sequences is generated by multiplying by some numbers. So 1 over 4 is multiplied by 1 over 2 times 1 over 2. 1 over 8 is multiplied by, they generate by 1 over 4 times 1 over 2, and so on. So then we will say each term is obtained from the preceding number by multiplying the same number to each of them. So 1 over 2 multiplied by 1 over 2. 1 over 4 multiplied by 1 over 2. 1 over 8 multiplied by 1 over 2 to generate the rest of it like this. So we call this one is common ratio. That number, that particular number is the common ratio. Like in this way, you can try to see the difference between here, for example. Okay, generated by multiplication of the some numbers again, similar. We call this kind of numbers, or sorry, series, geometric series. What does it mean? We have the just only one term or first term, then we know the rest by using the common ratio. We use the, okay, series notation to write them in the following way. For example, okay, this is equal to this actually 1 over 2. This is a first term, and the rest is 1 over 2 quasi n minus 1. This is the one. So this is the geometric series. Similarly, we had this, and we said this is the basically the first term is 3 over 5. You can see here the ratio or common ratio is negative 4 over 5. This is your
Prof,
answer.
sorry. Slide tak gerak.
Allahu Akbar. What is wrong? What is wrong? You can see now?
Prof, Fadia suggest jangan buat slideshow. Prof buat macam ni je.
Oh, okay. You mean just...
Kalau Prof buat slideshow, dia stuck.
Oh, okay, no problem. But at that time you will be able to see all of them, not the step by step. I want to show the step by step. No, never mind, it's okay. Now let's have a look at it again. Now you can see all that together. This is 42. Is it okay, 42? You nampak tak?
Nampak.
Okay, that's good. So, okay, let's look at, make some analysis on this. 1 over 2, we have the first term. Second term is 1 over 4. So how to generate the 1 over 4? We multiply the 1 over 2 by 1 over 2. Then we reach to the 1 over 4. Then 1 over 8 we have. How to get 1 over 8? We multiply the 1 over 4 by 1 over 2 to get the 1 over 8. So therefore, first term given to us as a 1 over 2, common number between those terms is the 1 over 2 as well, because, for example, 1 over 16 we generate by using the, or multiplying by 1 over 8 times 1 over 2. That is the one. 1 over 2 is the common to all. Then this is the representation or notation to use for this particular series by using the summation notation. Then similarly, if you look at the second one, 3 over 5, first term, okay, 3 over 5 is the first term. Then rest is, for example, 12 over 25. Macam mana kita boleh dapat dari 3 sampai 12? 4 kali. This is the 4. 5, kita dapat 25. Macam mana? Multiply by 5. So 4 over 5. But 1 here is, for example, we have the negative 1. So negative 4 over 5. Then negative kali negative, balik to do again the positive, negative, positive, negative, and so on. Is like this. In this particular case, common ratio is negative 4 over 5. In this one is much easier because if you look at it, the bawah tak bergerak is the same, 3, 3, 3, 3, 3. Atas sahaja 2, 4, 8, 16. So we multiply each of them by 2. 2 times 2, 4. 4 times 2, 8. 8 times 2 is 16. So 2 over 3 is the first term, you can see, and the 2 is the common ratio. This is the one. Now, how to find all these things? I mean, as a value or sum together. So we use this one basically. Now, if you have the Sn, or we call that one as partial sum, it is in the form of A, first term, plus A times R, plus A times R square. R square. If you go back here, actually, in here, this is 1 over 2. Here is square. Here, 1 over 2 times 1 over 2 square, and so on. As in here, you can see here, coming quasi of 2, 1 over 2 power n minus 1. Similar, we write that one as a like this, AR square plus AR cube plus ARn minus 1 is like this. Now, when you multiply Sn by the R or common ratio that belongs to everyone, we multiply each of the terms by R. When we multiply by each of the R, we will get A times R, we will get A times R square, we will get A times R cube, and so on. Okay? When multiplication by R, each terms we have. At the end, we have A Rn minus 1 times R, then it will be the ARn. That is the one. So now we try tolak Sn minus Rsn, meaning that we multiplied in all this one as a negative 1 and tolak the yang pertama or first one. Then we will have the first one is the A, tinggal sana. The rest is negative, 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 negative. All together negative. Kecuali tinggal sahaja A times R kuasa N. So kalau susun sikit, Sn is equal to the A minus ARn minus kuasa N over 1 minus R. Because if you take here common one as a Sn, tinggal sahaja 1 minus R, which is here coming as a, okay, the denominator, meaning that A 1 minus R kuasa N over 1 minus R. And R, of course, cannot be the 1. If it is 1, at that time is not convergent anyway. So now, if R is module R or nilai mutlak R is less than 1, the kuasa of the Rn goes to the 0. For example, 1 over 2 kuasa N is 1 over 2 to the kuasa N. Then 1 over 4 kuasa N, for example, is 1 over 3 to the kuasa N. In other words, when R is less than 1 or nilai mutlak R is less than 1, the Rn tends to the 0 as N goes to large number or N tends to infinity. So therefore, for the geometric series that we have, converge to Sn or partial sum is equal to the A over 1 minus R. Because this R kuasa N goes to the 0 bila kita ganti A over 1 minus R, subject to the nilai mutlak R is less than 1. So we can say geometric series is convergent if nilai mutlak R itu atau common ratio is less than 1, nilai mutlak. If it is greater than 1, is divergent. So therefore, have a look at particularly this. For example, 1 over 2 kuasa N minus 1, which is first term 1 over 2 over 1 minus 1, which is 1. First one is convergent. Second one, have a look at first, okay, 3 over 5 over 1 minus 4 over 5, which is 1 over 3. Second one is also convergent. Third one, if you look at it, 2 over 3, 2 to power N is macam mana? Yes, first term, 2 over 3 over 1 minus, okay, macam mana? Can you apply like this? No, because R is this time doesn't produce 0 kuasa. In other words, this property does not correct at that time if R is greater than 1. Kalau R greater than 1, its power will be increasing. For example, the 1 power is, okay, 1, 2 power is 4, 3 power is, for example, 9, goes on like that. So R kuasa N doesn't go 0. So therefore, at that time, if R is greater than 1, this is not equal to the Sn A over 1 minus R anymore. So you have to apply this. When you apply this, 1 minus Rn goes to the infinity. That is the things that we are trying to say in the last one. So therefore, series divergent because common ratio nilai mutlak is greater than 1. 2 greater than 1. Is that okay? Jalasta, any question? Okay, never mind. I will try to go one further and let's have a look at this repeating one. For example, I'm sure you have seen, I can give you all, slide, but you won't be able to enjoy how to write this one as a geometric series. For example, if you have the decimal numbers, this is exactly the same writing like this, 8 over, 8 over, 8 over, 8 over. When you look at it, is actually common ratio ada. So therefore, you generate the next one by multiplication of the 1 over 10 to the power 2. 1 over 10 to the power 2. Therefore, you can try to say like this. First term is the 8 over 10, and the common ratio is 1 over 10 to the power 2, or 100. Then you can look at it this way. Then therefore, it is again convergent. So therefore, it is equivalent to the 8 over 99. Let me go back to your things. Now you can try to say like this. First term is this, and the ratio is 1 over 10 to the power 2. Then when you apply since it is this one is less than 1, nilai mutlak is less than 1, so therefore you can apply the formula A over 1 minus R, which is 8 over 99. So you will be able to write those decimal numbers as some real numbers in terms of like this. Okay. So now, as a summary, I will try to give you as a summary, okay? When we have the infinite series, we look at the partial sum or first n terms, adding up the first n terms. If this one is convergent, series is convergent. If it is not, series is divergent. It's for the geometric series. For the geometric series, we have seen if R is less than 1 or absolute value of the R less than 1, then it is convergent. If absolute value of the R greater than 1, it is divergent, okay, for the geometric series. So today I will stop here. Then, okay, we will continue next week with some kind of new topics. Any questions do you have? Do you have any questions?
No.
Okay, please fill up your attendance. Please fill up your attendance and send through the WhatsApp again. And at the same time, if you have finished your exercises answer, you send to me. Do not use your friend telephone or do not use your friend email. Just send from your own email. Okay. Then I will tutup the today session. Then we will continue next week. And you will have, I think, the test, or I will talk to the madam first. Then she will arrange, because today is postponed because of this water in the campus. And we will let you know. Okay, take care. Assalamu alaikum. Welcome. If you
Thank you,
Thank you,
Prof.
welcome, welcome, inshallah. Okay, yeah, please. But at the same time, please try to read the notes that I have just sent to everybody. I send the Fatiha, then she can try to, I think, distribute to everyone. Okay, take care.
Okay, thank you, Prof.
You're welcome. Assalamu alaikum.